Now that we have seen how we can use boosting for classification purposes, wherein we have primarily looked at binary classification as well as multi-category classification. Now, in this session, we will focus on how we can use boosting when the response variable is continuous, which means for numerical prediction purposes, or in short for regression purpose, how can I use boosting? How will it really help me in terms of improving or looking at different types of predictions, especially for the numerical data? That is what we are looking at when we are talking about boosted regression. Here I want to talk about four different algorithms. One is an L2 regression, L1 regression. We will also talk about robust regression as well as quantile regression. These are the four different methods we would be looking at, and we would try to take a data set which has a continuous variable as the response variable, and try to build relationship between the continuous response variable and the various attributes, and see to what extent the predictability or the accuracy of the model can come out after the boosting process, right? So the data set that we are considering for this purpose is the insurance data set, which we have used for various applications earlier as well. Even in the decision trees, we have used it. Neural networks, we have used it. Support vector machines, we have used. Random forests, we have used. So wherever we had an opportunity to look at the response variable, which is a scale variable or a numerical variable, we have used this data set. We want here, just for a quick refresher for this data set, I'm just loading the data set again. Look at the dimensions of this. It gives me that there are 1338 rows and 7 columns, and a quick summary of this is telling me that charges is the actual dependent variable that or the response variable that I am talking of here, which would be assessed with respect to the age of the person, the sex, the BMI, the number of children. So how much charges, what are the charges of insurance would be related with the age, the sex, BMI, children, smoker, and region of that particular person. So that is what we want to build a relationship from the training, from the historical data of 1338 people for whom we have got the charges and some of the attributes associated with them. So we have built so many other models on the same data set, but now I want to see to what extent the various boosting algorithms that we are going to look at can really play a role in terms of doing an effective prediction of the charges based on these various attributes, right? So that's our task. We will be using all these four different algorithms on the top of it. So let's get into the L2 regression first. So wherever we are talking about L2 boosting, right? If you remember, we have used the L2 boosting even with our classification algorithms also. So in that, the objective was the error minimization. Here it uses the least squared error minimization. When I'm saying least squared error, the actual values minus the predicted values whole squared. This is the squared error. It will try to do the coefficients in such a way, the iteration specific coefficient alpha m will be adjusted in such a way that the overall least squared error is going to crop up, right? So this is what is the objective in an L2 regression, right? The objective is this error has to be reduced from iteration to iteration. As we have talked about boosting, in boosting there is always an error function. The error epsilon is computed using different mechanisms. In case of classification data, we have seen that the error is computed either as an exponential or logistic. So here we are talking about the error being computed as the least squares error. That particular error needs to be minimized. That is what is being done by the L2 boosting. Going with the R implementation of that, it is implemented using the package MBoost, and the method that we are talking of is GLM boost. Probably now from here onwards, whatever are the sessions that I am taking with respect to boosting, I will be taking 2 or 3 more sessions with respect to boosting. What you will observe is almost all of them will use the same package, same function. Only small differences exist, especially with respect to the family here, but different boosting algorithms do come up which can help us in doing different kinds of predictions. So probably this package is one of the wonderful packages from the perspective of boosting, and this particular function can do lots and lots of types of boostings altogether. So a good understanding of this algorithm implementation in R is very important for us. So let's look at that part. Let's install that package called MBoost. Okay, so let's load this MBoost package. Okay, package could not get loaded. Let me just close it and reopen it. Okay, now it looks like the installation is successful. So I have loaded. Now let me load this MBoost package. Right, now things are fine. Let me also load the data now. Loading the data. All right. So we have already loaded the insurance data. Quick check. Okay. So we have loaded the data. We have loaded the MBoost package as well. Now I want to see the GLM boost function. Now if I understand this function, I think for various methods in this session as well as in the upcoming sessions, we are going to use the same GLM boost function from the MBoost package. So there is not much there will not be much of a necessity to understand the function again and again. So quickly let's look at this GLM boost function. So it does a gradient boosting with component wise linear models. That is what is being done by this gradient boosting mechanism. Gradient boosting for optimizing arbitrary loss function. So here we are talking about a loss function which is least squares. Least squares error is my loss function where the component wise linear models are utilized as base learners. Now, if you look at the way we are giving the input to it, the GLM boost, initially I have a formula. So I can bring out my response variable, tilde, my explanatory variables. I am giving the data, which is a data frame containing the variables in the model. So I can specify that data. Weights by default, I don't need to give anything. The model will take care of them at a later point. All these things I can ignore. If there are NAs, what do I need to do and all those things. Control. The controls, I can very well specify the controls from the boost underscore control. Again, just like the way we have done the rpart underscore control, here we are talking about the boost underscore controls which give various other parameters as a part of that. Right, you could see the family, the control. So if you look at the boost underscore controls, these are the things. The family is Gaussian. The control is the boost underscore control. In the boost underscore control, we can look at so many, so M stop, an integer giving the number of initial boosting iterations. So by default, there are 100 boosting iterations that are performed. That is what we are giving as a part of boost control. New is 0.1. New is the kind of value between 0 and 1, which indicates the step size or the shrinkage parameter. So the default is too large for many applications with family Poisson, and a smaller value is better. So I can very well set a default not to 0.1, but probably I can set it to 0.05 or probably a 0.01, whatever. So which talks about by how much extent there should be a change so that the next step is typically proceeded. So we will set the new value, the shrinkage parameter for almost all the iterations. Then the risk we are looking at whether it should be out of the bag error that needs to be reported or typically the in bag. So with respect to the learning sample itself, if you have to compute the error, we are talking about in bag, and if it is based on out of the bag errors, then the over bag is typically provided. And trace is false is telling me that it will not print out all the steps that it has typically taken. So those are some of the things that we give as a part of the boosting control. Right, I'll use it from the boost underscore control, but this is the one that I'm going to do out here. The family is very important for me. Where is my family? So here you go back to MBoost underscore fit. The family is very important. Right now we are setting the family to Gaussian, and that is what is the L2 regression all about. But if you look at the family, it will support a big list of families. So this is where all our future models are going to come out. Right, we have a binomial link, binomial where link is logit and probit. Right, we can look at different kinds of families. So in the L2 regression, we'll use the family as Gaussian. But when we are moving on to L1 regression, I would be using the same, but where the family I would be using as Laplace. I would be using the Laplace family for L1 regression. All else might remain the same to a large extent. I would be using the family as Laplace there in L1. And similarly, when I am using the robust regression, the third one, I'll be using the family as Huber, this one. Huber is something that I would be using. And similarly, when I am executing a quantile regression, there I am talking about the quantreg, this one. So what you could typically see is the four models that we are discussing out here. It's the family that is going to change quite heavily compared to many other things. So that is how we are giving as an input to this particular model. So let's try getting started. Try doing the fitment part, right? The process still remains the same. We have the data in front of us. Now I need to split the data into a training data and a testing data. So let me set the seed to 1000. Then let me use a variable called train, wherein I am using a sample function 1 to 1338. 937 is the 70% of that. So let me take 937 as the sample. 937 numbers between 1 and 1338 randomly I am picking, where the replace is set to false, means no duplication. Now training data for me is a subset from insurance, wherein I will be including the rows that are there as a part of the train and all the columns. And my test data is again a subset of insurance, where I will be using the rows that are not there as a part of the train, but I'll take all the columns. So that's how I am splitting my training data and the testing data. Now I am ready for going ahead with my model. So I'll simply say fit, where I would be using the GLM boost function. So I'll take the GLM boost. The formula to start with, charges is my response variable, tilde dot. That's my, all the other variables are my explanatory variables. So I have considered this as the formula. The data is coming from training data. So that's where I'm calling data equal to train data. What else do I require? Weights I don't need, any action I don't need, contrast that I don't need, center I don't need, control equal to boost underscore control. So I have to specify the control. Either I can take all the default parameters. So if I want to be slightly careful of, let me just check what are all the default parameters that it is having. mstop is 100. So I can just set the number of iterations, boosting, initial boosting iterations, I am setting it to be 100 itself, right? The new value I am setting it to 0.1, the default. So everything, if I am setting by default, I can just go ahead with the boost as it is. So I'll keep the boost dot controls to be the default itself. I'm not touching that. Then what else? Design, vector of spaces, and dot 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 are the additional arguments that you are passing on to the MBoost fit. So in the MBoost fit, what else can we give? Weights I don't need to give, offset I don't need to give, family is very important to me, as I have specified. For this model I will specify the family as Gaussian. In case of L2 regression, I will specify the family as Gaussian. And controls, anyhow we have given the boost control, the default itself. So that's it. I don't need anything more for running this model. So I can very well execute this model. What I want to do is I will save this to a notepad, because the next models, it's just a matter of changing the family to a large extent. I don't think, though I have the option of changing some of the boosting controls to bring in the dynamicness, I'm just taking the default, but I can change the number of the shrinkage parameters, etc. And I can play around with the models to see where the model is giving me a much better fitment. So for the purpose of understanding here, I'm just leaving them the boosting controls to be the default controls itself. But the family I am setting as Gaussian for the purpose of L2 regression. So now let me go back to my slides, see to what extent we have executed it till now. We have loaded the MBoost package, done. We got the data into R. The response variable is a numerical continuous variable here. We have split the data into training set and testing set randomly. We have done that. We have fitted the model using the GLM boost function. So the number of boosting iterations, we have left it to the default where 100 iterations would be performed. The shrinkage parameter also we have left it to be the default from the boost underscore control where it would be set equal to 0.1. Now this is where the model is getting fitted. So let's continue the fitment of the model. Looks like the model got fitted. Now I can go ahead in terms of understanding the coefficients of this model. I will look at the coefficients of this model. Right, my model got fitted. Now I am going ahead with the coefficients of the model. So it says, as per this, the charges are intercept minus 23,836 plus 240 times the age plus 300 times the BMI, 355 times number of children, 230 to 23,305 times the smoker status being S, minus 95 times the region if it is southeast, minus 48 times the region if it is southwest. So that is how the whole model typically came out. Right, this is what is coming out through the model using this GLM boost. Now, so we have looked at the coefficients out here. Let me see what else did I talk of here. So we have used the coefficients. So here we don't have a few coefficients. If I could see, there are only 5 coefficients that have come out. Sex did not come out as the coefficient here in the model. And even the regions, only 2 regions have come, southeast and southwest. Northeast and northwest have been treated more or less similarly. So there are 2 variables that did not come out at all with respect to this model. Fair enough. Now this is with one set of data, right? So this is where I want to look at the cross validation. Now first of all, I don't know whether 100 iterations is sufficient for me or not, or is it like as in some cases if the number of iterations is increased, the error also gets increased, right? So too many iterations is also dangerous, too few iterations is also dangerous. So this is where I want to be a little bit careful in terms of choosing my number of iterations. So this is one place where I want to look at the tenfold cross validation, right? So I want to see where the error is coming out to be the minimum most. Now for this purpose, right, I want to take the tenfold cross validation mechanism. So the cross validation I want to execute using a function called CV. So let me just check what is coming as a part of this CV. CV and CV res, two important things here. First we have to build a CV object. So if we see here in terms of CV, it takes the weights, right? In case of CV, it takes the weights. So I can take the weights based on the model itself. So if you look at the model, I can see model dot weights. I can look at the model dot weights of fit. If I am looking at the model dot weights of fit, by default I have given 1 as the weightage. I did not give the weightage at all. So I can, if I say model dot weights of fit, so the weightages are giving in that way. If I have a different weightages set, I can very well give those kind of weightages as well. But model dot, so here if we see in the CV function, the first thing I have to give is weights. So I can very well give model dot weights of fit. Then the type, I can set it either to bootstrap or k-fold or subsampling. Right, when you look at the type, I can set to anyone. Character argument for specifying the cross validation method. So generally now we are doing a 10-fold cross validation. So this is where I can set it to k-fold. And because I am setting it to k-fold, I have to specify how many. So by default, if you see, if it is k-fold, it will be taking as 10, otherwise it will take as 25. So because it's a 10-fold cross validation, the default is coming out to be 10 itself. So as long as I am doing 10-fold cross validation, I really don't need to give this explicitly, because it will take the value as 10 itself. So based on that, I'll have to first create a CV function, and this CV function I will give as an input to the CV risk function. So if you look at in the CV risk function also, it is taking me the boosting method, but the folds, it actually wants the CV model. The CV is what should go as an input to this CV risk function. So that's where I have to first compute the CV. Either I can do all of them in one single shot. CV risk is the function I am more interested in to typically identify. The CV risk function is more important for me to identify how many iterations are more appropriate for this model, right? So let me give fit CV as the name of the variable, wherein I want to capture the CV risk. I want to compute the CV risk function. The object with which I am doing that is the fit object, which is what is coming from my MBoost. But the second variable, which is folds has to come from the CV model itself. So this is where I can say folds CV. The CV first takes model dot weights. So I can very well take model dot weights of fit as one of the inputs to it. And the second input that it takes is the type. The type I can set it as k-fold. The type I am setting it to k-fold. So this is the code that I am maintaining. So the fit, so it is typically taking the CV risk. The fit CV for me is taking the CV risk function. The CV risk function requires, what is the CV risk function doing for me? It is calculating the empirical risk, right? And I'm looking at the optimal stopping criteria here. The optimal stopping criteria is that particular iteration where the overall average risk is typically minimized. So this is actually performing a CV risk, which is nothing but cross-validated estimation of empirical risk for hyperparameter selection. So it is estimating the empirical risk for different kinds of iterations, for different iterations. And what you could simply see is, I'm more interested in looking at where it should stop the iteration. So let's see whether the cross-validated estimation of the empirical risk is taken place with this code or not. I'm taking a CV risk where I have fitted the model. The folds, I'm looking at either it should be a bootstrapped or it should be a k-fold. So here, because it's k-fold, I have selected it as k-fold and I have taken it as a 10-fold. So I should have said b equal to 10, but by default b will be taken as 10 if it is k-fold. So that's where I did not give any kind of specification again. So based on this, the fit CV is executed. So let me save this fit CV also as a part of the model. Now if I see what is coming as a part of fit CV, I could see it's a cross-validated squared error. So since I have said 100 iterations, this is how in each of the iterations the squared error is typically coming out. Right, this is how the squared error has come out in all the 100 iterations. So I want to see, right, probably can I do the plotting of fit CV? I don't think so. Yeah, there is a plotting of fit CV that is possible, wherein I could see where the error is actually coming down. Squared error regression for number of iterations. So it could see that somewhere here the error is coming out to be the least possible. There is a line that is drawn out here which shows where is the squared error typically coming down. But at the same time, so let me do the plotting of this fit CV also for all the observations. Then at the same time, I use another function called mstop. Mstop is the method for model fitted by boosted algorithms. So I will typically get when I am giving the CVM, when I am giving this fit CV as an input to it. If you see mstop of fit CV, it says at what location for what iteration I am getting the least possible error. So it is saying that I am getting the least possible error for the 99th iteration. Out of the total, for the 99th iteration, I am getting the least possible error. So based on this, I am going ahead to understand the 99th iteration from my model itself. So from the fit itself, I am taking a subset of this one, which is typically telling me in the 99th iteration what are the coefficients that are associated with the 99th iteration. Right, the whole 99th iteration is being shown. This is the loss function. I am looking at the overall 99th iteration saying that these are the coefficients, this is the age factor, this is the BMI, children, smoker S, region southeast, region southwest. So these are the coefficients that are coming out. So we could see that 6 variables and 1 intercept overall for the model. Now this is what is the fitted model based on the number of iterations as 99. Let me go back to the slides again. So here we have optimal stopping. The optimal stopping is empirical risk we have calculated using CV risk. The optimal stopping is the one that minimizes the average risk which has occurred at the 99th occasion. So I have used the fit of mstop, which is telling me that at the 99th iteration I am stopping and I am fitting the model. So based on that I got the coefficients that are associated with the 99th iteration. Then I am going ahead with a confidence interval computation also. I can do a bootstrapping, and based on the bootstrap I can actually look at the confidence intervals, let's say the 90% confidence intervals. I can very well go ahead with a 90% confidence interval, which means it will give me the lower, which is the 5%, and upper, which is the 95% for each of the attributes. So if I say conf int, wherein I am doing the fitment, the fit is what I am taking, or probably here the bootstrapping. If you look at the conf int, you will get some more clarity here. Computes the confidence interval for one or more parameters in a fitted model. That is what is being done by confint. It is not specific to MBoost. It's actually coming from the stats package itself. So for every parameter, if I want the confidence interval to be fitted, I can say confint. So I have to set the object. So here I will set the fitted object is what I will set, and I have to specify the level. The level, if I am setting 95, By default it is 95, so if I want to ignore it, I can ignore this. So it will set 95, which means it will compute the 2.5% as well as 97.5% interval, because the gap will be 95 there. The parameter, the specification of which parameters are to be given in the confidence interval. So if missing, all the parameters will be counted, that is fine. But additional arguments for the methods, we are talking about a bootstrapping where we can set the bootstrapping to 100 or probably thousands. Bootstrapping should be done with a large sample size itself. So let me just see now. Conf int. I want to take the confidence interval of each of these. So I am taking fit. The confidence interval, I am setting it to 1000 and I am leaving the level to the default of 0.95 itself. Now based on that, let me see, it will take some time because the process will execute 1000 times. But yes, I mean, just to showcase, I could have taken it as 50 or 100. So we can get the confidence interval for each of the predictors. If it takes too much of time, we will reduce it to 100 or 50 so that we can just quickly understand the process. Because the whole process will take 1000, will be executed 1000 times. Let me just pause the recording until it gets executed. Let me just check if I repeat this with a very few number of bootstrap samples. Let me just set it to 50 so that we will understand a little bit more. Okay. When we have set it to 50, it looked much faster, much easier. Now you could see here the classification for age. The interval is between 212 to 261. For sex, it is between 0 to 638, and that's the reason it did not get included, because there is a possibility of 0 as a part of the group. Similarly, BMI, the coefficient is ranging anywhere between 240 to 355. For number of children, it is between 85 to 671. The smokers being yes, anywhere between 21,000 to 24,000. And regions associated with northwest, southeast, southwest, these are the typical ranges. Right? Now, using this model, I want to go ahead with respect to my prediction to see how accurate are my predictions. So I am using the predict function, right? If required, I can omit the confidence intervals for the next of the models, because I am more interested in looking at the goodness of fit of the model overall on my test data. So I am using the fit. The new data for me is my test data. So I want to launch this on the test data to see the accuracy of the model, and I want to look at the response. If I don't give the response, the prediction is coming out to be, it gives me all these values that are associated with every observation in the testing data. So this is what is the outcome that is coming out for every observation on the testing data. Now let me copy this code as well. Right, I can very well look at, first, after identifying which of the variables after identifying how many iterations I really need to stop, I don't need to get into the identification of the significant, identification of the confidence intervals associated with each one of them. And once I am done with this part, I can very well get into the prediction process. I have predicted using this, and once I know the predicted values, I can very well compare the predicted with the actuals, find out the R squared. So correlation with respect to the predicted value, I have to take it, let's say predicted value. Let me just check what comes out. I want to look at the correlation between the predicted and the actual is coming out from test data and the seventh column of the test data. I'm taking the square of this correlation, which is giving me only 78.32%. If I'm using this model, right, if I'm using this model, the accuracy is coming out only to the extent of 78.32%, which we did not get it that much better compared to what we have looked at when we have used other methods like neural networks and random forests, etc. So in this case, looks like the L2 boost did not work out that heavily for us, right? L2 boost did not work out that heavily for us. That is what we could make out here. But it would have been better if I had redone the model. Let me just check if there is some difference. If I am using fit dot, so instead of going ahead with the prediction like this, let's say if I am going ahead with the prediction wherein I would use not the fitted model, but I would use this part where it is more and more optimal. Will the fitting actually happen? Yeah. Let's see if there is some kind of a difference in the result that we are going to get through this process, where the optimality has actually come. Looks like it is 78.32 itself in this process as well, right? So even if I am doing the prediction based on the fitment that has happened at the 99th interval, even still the result is coming out to be the same itself. So I can very well look at this particular aspect here and overall look at the accuracy of the model. So in this case, once I am looking at now, identify the significant variables. If I am doing a confidence intervals, I can very well make out which variables are significant and which variables are insignificant. That we have anyhow made out when we have simply looked at when we have simply looked at the model. Only those variables that are included in the model are significant. Those variables which are not included as a part of the model, they are going very insignificant. So we are doing the predictions on the testing data, and based on that we have computed the squared correlation coefficient. In this case we got 78.32% as the accuracy of the model, right? So that is what is the accuracy of the model going with L2 regression. Now let me try out the other forms of regression, right? I can very well try out the L1 regression now. The second model in this context is the L1 regression. Now if you see here some of the basic differences when I compare it with L2 regression, where L2 regression, sorry, this is L1. So in case of L2, we were minimizing the actual minus predicted whole square, which is the least squared error. Whereas here we are talking of, we are trying to minimize, L1 boosting is trying to minimize the least absolute deviation, actual minus predicted. So it is trying to look at minimizing this, whereas the L2 regression was trying to look at minimizing this. So some of the absolute differences between the observed values and the estimated values. And because this is squared, if the deviations are much higher, their squares would be a much impacting thing. So that's where they are very sensitive to outliers. Whereas in case of L1 regression, the sensitivity to the outliers is much lesser. The L1 regression is more robust to outliers compared to the L2 regression. So this is one place where we may have to see if this is providing some better estimate compared to your L2 regression. Now if you see, everything is the same. We are using the same MBoost function, MBoost package. GLM boost is the name of the function. The only thing is the family is what we are replacing with Laplace. Laplace is an indication of L1 boosting, whereas Gaussian is an indication of L2 boosting. Laplace is an indication of L1 boosting. Apart from that, if you see, the model is the same, right? We will first read through the steps so that we can go ahead and directly implement. We have to load the package, get the data, training data, testing data, find the model using the GLM boost function. We have set the boosting iterations as 100 to start with. Shrinkage parameter is default zero point 0.1, the new value. So we have to choose these two things so that the overfitting can be avoided. So initially we will set something, but we have a method where we are doing a tenfold cross validation process. We are estimating the empirical risk using the CV risk function, and based on that we are trying to see where the number of iterations need to be stopped, and that is what we are using as a model for the fitment purpose. So based on that, you could clearly see that the steps that we are executing here are more or less on the same lines as the L2 regression that we have executed earlier. Even this is a typo error. I am calling this as L1 regression. So based on that, you could do the bootstrap confidence interval. You can identify the significant variables, you do the prediction on the testing data, calculate the squared correlation coefficient. So we can use that text file that we have used. Instead of Gaussian, I want to use Laplace. That's the only difference. Let's go ahead and see if we can implement L1 regression, and if we are implementing it, what is the result that is coming out. Okay, the L1 regression is implemented. Look at the fit. The fit is saying, so it has looked at the error function is absolute of y minus f, which is the actual minus the predicted. The if you see here, the coefficients are something significant. It has taken only intercept and the smoker status. No other variables are considered by the model. Probably something much different. The L2 regression has considered so many parameters, whereas you see the L1 regression has considered only the smoker status as a significant variable impacting the insurance charges. None of the other variables are typically being considered, especially when your shrinkage parameter is zero point 0.1. So this is where I may think of reducing my shrinkage parameter and even trying it out, right? Probably if required, let me just set new equal to 0.01. Just change only the new value from the base, change it to something else to see if the model has improved in any way. Even still, I see that okay, there's a small change in the coefficients, but I could see that the parameter that is being considered is still only the smoker S. So probably, yeah, if you want you can change it, otherwise let's keep it the default itself. So this is considering that only the smokers, only for the smokers the charges are much higher, and for non-smokers the charges are much lesser. That's the only indication this model is giving. So even if I go with the coefficients of it, I should get the same answer, right? I am getting this much. If I go with the summary of it, so the summary is also telling me the same story. Only one variable has been shortlisted for the process. Now let's try understanding whether the 100 iterations are necessary or somewhere I can cut short on the iteration. So this is where I am executing my CV risk function to understand the empirical risk of the model across different iterations. So for different iterations, the empirical risks have been computed. So looking at this fit CV now, wherein for each of the iterations, I am seeing what is that cross-validated absolute error. Looks like across the board the error is more or less similar, 8536 point. So that is what is the error, cross-validated error across, because it's only one variable that is being considered. So even when I am looking at the plotting of this, I see that the error is more or less similar. It's only at the 100th iteration or somewhere the error is coming out to be the least, probably 0.223. So there is a very minute change in the absolute error from iteration to iteration. So even if I have to stop, it is stopped at the 100th iteration itself. So based on the 100th iteration, if I have to fit the model, I should get the same coefficients again, 1.265 times this. So I'm going at with this kind of a model fitment overall. And if I'm doing the prediction based on this, the prediction is done. So I can very well look out for the R squared between the predicted values and the actual values. This model L1 regression boost is only giving me 63.88% accuracy, which is a much poorer accuracy compared to various other methods that we have used till now. So in this case, L1 regression is not doing any kind of a good thing for the model. But of course, in some cases, these are all different kinds of aspects that I may have to try. In some cases, this can definitely give me a much better result compared to other mechanisms that I'm using, like neural network regression, support vector regression, or any other aspects per se, random forest based regression, etc. Now moving on to another mechanism on the same lines, which is the robust regression. This uses a Huber loss function. Right there, in one of the cases, the loss function was actual minus predicted whole squared, least squared error. In the L1 regression, it is the absolute error. Now here the loss function is a Huber loss function, which is also less sensitive to outliers compared to the L2 regression. L2 is very sensitive to outliers. Both L1 and robust regression are less sensitive to outliers. And even here we are looking at using the method Huber as a part of the family, and rest all remaining the same. If you quickly look at it, we have loaded the package, got the data, training and testing data. We have fitted the model using GLM boost. We have set how many boosting iterations initially, what is the shrinkage parameter, got the coefficients of the model, done the tenfold cross validation, which will help me in identifying how many optimal number of boosting iterations are required. So we are computing the empirical risk using the CV risk function. Based on that, we will see at what number of iterations the error is the least possible. So that is what that number of iterations is where we are choosing the model, and we are stopping the number of iterations and fitting the model. And that model will be used for the prediction purposes on the testing data. The optimal model will be used for fitting on the testing data. Whatever the model that we have got as the least error kind of a model, that is the model we are going to fit on the testing data. Based on that, if I want, I can even plot the predicted and actual values. As at the same time, I could also find out the R squared of the model, see what is the accuracy associated with it. So all the things I'm changing here is the Huber. I'm changing this to Huber. Rest all remaining the same. So let me execute the model again. So this is where I'm going ahead with the Huber model. I'm looking at the now let me see what is this model given, the FIT, which is a robust regression model. So this has considered three variables at least: age, number of children, and smoker status. It did not consider BMI again. Now if you see the Huber function, it is looking at the median of the absolute difference between the actual minus the fitted value. So that is what is the Huber error. Going with this Huber error minimization, I could see that the age is given a weightage of 242. Children have a coefficient of 135, but it's again the smoker status which is carrying a much bigger value. So this is how this model is designed, right? Even when I go with the coefficients of it, I will get these numbers itself. Now let me assess the empirical risk of the model across the different validations, across the different iterations that we have performed. So across all the 100 iterations, it is looking at what is the empirical risk of the model based on the 10-fold cross validation that we have initiated. Now it has come out with the Huber error across with all the different sets. So I could see here it is the error is to the extent of 32 million, 31 million, 30, 29, 28, 27, 26. 25, it has come down to 13 million, 10 million, right? It has came down to 6 million, 5 million, 4 million, 3 million. Now you could see that the error has been decreasing all the way through. So if I want to do the plotting of fit CV, it looks like the error has been falling all the way through. So at 100 iterations only, I could see that the error has come down quite drastically. So in these cases, I may even think of increasing the number of iterations to see where the error is coming down even more drastically. So I know if I have to stop this particular model, it has come down at 100 iterations itself. And based on this, if I am going ahead with the prediction part, it says the predicted values. If I'm looking at the correlation between the actual and the predicted values, this model is giving me around 74.9% accuracy. Probably only if I'm looking at these models per se, right? If I'm only looking at these models per se, the L1 regression is very horrible with 63.88%. L2 regression has given me 78.32%, whereas the robust boosted regression has given me 74.91%. Probably I should change the new values. I should change the number of iterations to really play around to get much more better predictions of the overall model. Otherwise I may have to change the otherwise I have to change the overall techniques itself. The boosted methods are not giving me the necessary mileage compared to the other methods like random forests or all other methods, neural networks, support vector machines, etc. Now in this context I am also looking at one more algorithm, which is the quantile regression, wherein as we have done the quantile based versions earlier also in case of random forests, etc., we are trying to build the relationship between these are the independent variables that I am having and this is the response variable. I am not looking at a mean to mean kind of a mapping here. I am looking at different quantiles of the response variable. So I want what could be the 5 percentile value, what could be the 95 percentile value, rather than just getting the conditional expected value of y given x. So rather than just getting the mean value, I am also looking at the different quantiles as a part of the estimation. So it is giving me a more complete picture of the conditional distribution of the response variable, especially where I am having both lower and upper quantiles, or if I am more interested in different kinds of quantiles compared to just getting one single value. So this is something that we can accomplish again using the same package, same algorithm, everything remaining the same. If you see the mechanism, the only thing is the family is changing to Quantrec, load the MBoost package, get the data, split it into training and testing. Now, estimate different quantile regression models by specifying the tau value to the quantile regression. So, instead of simply saying Quantrec, I would be specifying my tau value. If I am saying within the Quantrec, if I specify tau equal to 0.25, it means I am fitting the value at 25. I want to get a 25 percentile value, and if I am setting the tau equal to 0.75, I want a 75 percentile value, or the third quartile fitment of the model is what I am trying to do. And the same logic goes for all of them. So if I want, let's say a 5 percentile, for this case, let's say I want to get a 5 percentile estimate, a 50 percentile estimate, which is the median, and a 95 percentile estimate, which is the high end value. I want these three things to be predicted, so which means the same job I have to do 3 times. I will get different coefficients for each quantile. For 5 percentile, I'll get a different coefficient. For 50 percentile, I'll get a different. And for 95 percentile, I'll get a different. I'm doing a 10-fold cross validation for each of these three models. I'll use different CV risk functions across each of these models. So I'm going to get different fitments for each one of them. So if I want, I can calculate the confidence intervals in each of the cases, and how many iterations, after how many iterations I have to stop them. Even I have to give that particular aspect as well, right? In some cases, when my data is so high, it's better to increase the number of iterations rather than just sticking with the default one of 1000 itself. It's better that, I mean, default one of 100. It's better that I increase the number of iterations as well. So here, if you see the iterations in this model MBoost, in MBoost, the number of iterations, sorry, in the boost control, I can set M stop instead of 100, probably I can increase it. Otherwise, in some cases, the number of iterations may not be sufficient. But for our understanding, I'll still keep it to be the same. The only difference now I will bring into our model is, instead of just keeping it Huber, I want to do it as Quantrec. Instead of Huber, I'll set it to Quantrec, and I'll set tau equal to 0.05. So first let me do it with 0.05, the whole model. Then I'll do it with 0.5, and then I'll do with I will do it with the 95. More interesting part will be 0.5 only, because I can find the correlation squared and all only with respect to 0.5, not with respect to all the other values. So let me go ahead and see how this model is going to come out. So we have fitted this model. When I'm looking at 5 percentile values, it did not take any coefficient at all. Only the intercept came out and nothing came out of the model. Right? So it did not take any coefficient as a part of this quantile regression. And even when I am doing the CV risk assessment of the various k-fold, 10-fold cross validation also, probably if you look at the error, there is no, I mean, the error has to be more or less constant across, because there is no variable that is involved in the model at all. So it is like more or less on one single side itself. When you are talking about the plot, it's the same plot across. There's a flat thing, no reduction in the error. It's only going with the 100th iteration, where there is a very, very minute reduction in the overall error. So the same logic now I want to execute it when tau is 50, because we want to do the prediction also based on all the aspects. So let's say if I want to do the predictions, you look at the the spread on the lower side, it will give me that for everyone these are the same charges, because except the intercept nothing is being considered as a part of the model. But now if I go on the higher side, let's say with 0.95, let me see on the higher side if there is some kind of an improvisation with respect to the model. Right, if I am going with a 95 percentile value, I would like to see, even in this case also I could see that this is the only parameter, especially if I am going with 100 1000 100 as the number of iterations, even here it is coming out to be the same number for me, right? So which means the coefficients, even if I am doing a 10-fold cross validation, there is not much of an improvement for me. The 10-fold cross validation is more or less having the same kind of an error altogether, and when I am doing the plotting of it, I could see that again the error is more or less similar. And going ahead with the prediction part for this, the prediction part is also giving me that across the number is going to be 9451. So on the downward side it is giving 9442, and on the upward side it is giving 9451. Probably it looks like this quantile regression model has not worked in any way with this particular data. Right, all other models have been more or less appropriate for this, but looks like the quantile regression model did not do any good job with this particular data. Probably I may have to either increase the number of iterations, but still I don't see any kind of a change that is cropping up. So now even when I'm going with tau being 0.5, I don't see there will be any kind of a big change in the result. So in this case there is no advantage that is coming out with, oh, at 50% at least it looks like the smoker status has typically come out as an input. Right, the smoker status is coming out as one of the inputs to the model, and if I am looking at 10-fold cross validation here, it is slightly coming out that the error is coming down slightly. Right, across the error is coming down slightly, so I could clearly see that in the 100th iteration itself the error has come quite drastically down. The predicted value through this process is coming out to be this much, and when I am trying to find out the R squared between the predicted and the actuals, this is also working at around 63.88% itself. So for this model, even the quantile regression is working at 63.88% accuracy. Even the earlier models, the robust was at 74, L1 regression was again at 63.88, and L2 regression is at 78.32. So these are the different kinds of estimates that have typically come out using the different models that we have used by using the boosting as an alternative out here. Here the main focus was using different algorithms associated with the boosting, and based on that identify the key variables which can really help us in terms of building the model more and more effectively and doing much more better prediction. It looks like for this data many other models might do a much better job compared to the boosting algorithm. So even here it is very clear that there is no one single model which is a universally accepted best model which can do a much higher accuracy in terms of prediction of a particular variable. Very evident here. Though we have used more sophisticated boosting algorithm, we could see that the accuracy could not be improved beyond a certain percentage on the testing data. So these are some of the things which I wanted to touch base upon, especially relating to boosting, the boosting associated with numerical predictions. If you have any further queries regarding this, you can very well get in touch with me by giving me a call on the number that I have given below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.